Very good morning, and today we are going to discuss the topic titled Demonstration of PHIL experimentation for symmetric and asymmetric fault analysis of grid connected DFIG wind turbine. In this module, we will discuss the very detailed explanation of power hardware in loop experimentation. The power hardware in loop, popularly known as PHIL testing, involves connecting real power hardware to the simulated network in a closed loop. Now, the power hardware in loop simulation, power devices such as renewable generations like wind or solar and their inverters that are part of the system network are interfaced with the simulator that is run on the real time digital simulator in power hardware in loop experimentation. Power is exchanged between the RTDS and the external device via a power amplifier in the PHIL. Now, looking into the DFIG hardware setup, digital to analog D2A converters are used to convert the RTDS voltage or current signal into analogous signals at electronic level with a voltage range of plus or minus 10 volts and current drive in the microampere range. Such voltage and current levels are much below the test power devices operating voltage and current range. As a result, in PHIL simulation, amplifiers are needed to scale the signals sent from the RTDS to those needed by the test equipment. Also, to bring to your notice that due to the external devices integration into the power system network, the stability and accuracy of the interface are significantly influenced by the timing and quality of the signals sent back and forth between the devices and the simulator. Digital simulators like the RTDS, which employ the electromagnetic transients algorithm, can mimic the network reaction in a time step as quick as 50 microseconds. The interfacing DFIG device, that is the part of the network, requires the exchange of voltage and current between the digital simulator and itself. The current that results due to the application of the voltage to the external device is measured and sent back to the simulator. The sensor is used to sense the signal from the physical hardware device and feed the signal to GTAI through the power amplifier. The test demonstration of GTAI card. Now, we will see a small test system that is used to demonstrate how the signals from voltage or current sensors feed the signal from GTAO, GIGA transceiver analog output card and GTAI GIGA transceiver analog input card of the RTDS. In the function generator, we generate AC signal of RMS 3 volt and feed to the GTAI analog to digital converter card. The GTAI card is an 12 channel RTDS hardware component which is mounted in the cubicle. This signal is reflected in the RSCAD runtime and is received by the GTAI digital input component in the RSCAD. It is to be marked that the function generator can be thought to be input of voltage or current sensor sensing signal from the power hardware device. The device can be high power rating device like solar or wind generation or battery, or even we can think it as a EV charger. If we give this signal to another controller to generate PWM pulses, it will be a control hardware in loop. Let us see this small demonstration in which a 3 volt RMS sinusoidal signal input is set in the function generator. The signal is then sent to the GTAI card of the RTDS. The GTAI module in the RSCAD receives the signal and can be seen in the runtime of the RSCAD. Let us check the signal in the RSCAD runtime platform. If we now change the voltage to 4 volt, we see the change in RSCAD. Now, in case of test demonstration of GTAO card, the next demonstration is to show the working of the GTAO card, which is basically a digital to analog converter. The signal from RTDS is scaled in the software RSCAD GTAO analog output component, which is then sent to GTAO card. The GTAO card is a 12 channel RTDS hardware component which is mounted in the RTDS cubicle. Inputs to the GTAO model are IEEE 754 double precision floating point numbers. This model converts and scales input signals to 16-bit integers and writes them to the GTAO card via the GTIO interface. All the output signals are sent to the DA converters on the GTAO card at the same time in aligned fashion. The GTAO card's output range is plus or minus 10 volts. Inputs to the GTAO component must be scaled to produce a desired voltage on the output channels of the GTAO card. To show the receiving of the signal from the RSCAD platform to the hardware platform, we have shown a small demonstration where signal received from the GTAO card is shown in the oscilloscope. You can see the RSCAD platform where a sinusoidal voltage is generated, and using the slider we can set the magnitude of the waveform. the node voltage is given to the GTAO module in the RSCAD. The oscilloscope reflects the signal behavior that is received on the GTAO card. Here we had set 4 volt magnitude sinusoidal signal that is shown in scaled down form in the oscilloscope as GTAO card's output ranging from plus or minus 10 volts. We can vary the magnitude and similar trend of variation can be seen in the oscilloscope too. In the PHIL experimentation, the CRO is replaced by the power amplifier, which in turn amplify the signal to make it appropriate for the working of the physical hardware. Now, moving forward, let me demonstrate you the PHIL experimentation using the wind emulator present in our laboratory. As you could see the DFIG hardware setup, a DFIG WTG of rating 2.2 kilowatt hardware setup is connected to the distribution network simulated in the RTDS via a power amplifier. In the network we can see in unit 3 a utility grid of 11 kilovolt that is supplying through the transformer and providing 0.4 kilovolt to the bus number 3. The bus number 3 is then connected to power amplifier using a GTAO card. In the power amplifier, the mode is set to external to receive signals from the GTAO card. We can see the voltage reflected in the panel. The voltage is fed to the main supply of the setup. The voltage generated at bus 3 of the network simulated in RTDS is scaled using the voltage gain and is applied to the DFIG wind system via the amplifier. The main and the rotor branch circuit breaker is switched on and the DC link is charged initially to 317 volt. The power amplifier voltage information is passed to the PLL of FPGA controller to extract grid phase angle. Then we enable phase locked loop and check the reference theta with the phase A voltage. Once the DC link is charged, we enable the GSC control to maintain the desired DC link voltage, which is set say 30 volt greater than DC link voltage, that is 350 volts. The rotor of the DFIG is rotated at 900 RPM, which is 10% of the slip, with the help of the DC motor. Further, the DC motor is governed through armature voltage control method by using the chopper, thereby emulating wind characteristic. In this case, the wind velocity is close to 7 meter per second. Initially, the RSC is called to obtain recovery voltage and phase angle such that the DFIG wind system synchronizes with the grid by closing the relay contact. The runtime of the RSCAD platform is shown. First, the system is run on the open loop, that is wind emulator output is not fed back to the system as the grid is not synchronized with the stator of the DFIG. After the grid synchronization, RSC is optimized to extract maximum power at the operating wind speed. Now, we can close the loop to form the power hardware in loop. Moreover, during normal condition, the 2.2 kilowatt of DFIG is used to feed 25 kilowatt of active power to the distribution grid simulated in RTDS via power amplifier. This is possible with the gradual increase of current fed to the RTDS. The behavior of the DFIG system is analyzed during symmetrical fault case 1 and asymmetrical fault case 2 in the distribution network. In order to test the behavior of the DFIG wind system at the most severe unbalanced voltage, the phase to phase asymmetrical fault is considered in the analysis as the phase to phase fault results in a larger negative sequence component in the voltage than the single phase fault for the same depth. Further, a comparative study has been carried out to realize the severity of the asymmetrical fault with respect to the symmetrical fault. The DFIG wind system is exposed to the symmetrical fault with dip in the stator voltage of 50% of its nominal value in each phase for 5 cycles, that is 0.1 second duration. The PHIL experimentation results is presented in the figures. The voltage dip at first affect the stator flux as it is connected to the grid directly. The sudden transition in the stator flux induces high rotor voltage whose effect is reflected in the RSC and GSC current as disturbance. This disturbance in the converter current leads to overshoot in DC link voltage. Phase current and corresponding voltage variation is obtained from RTDS, result that highlight the symmetrical variation in all the 3 phases. The active and reactive power variation during the fault can be observed in figure shown below. The DC link voltage for both symmetrical and asymmetrical faults appears to be constant in figure because the voltage scale per division chosen is 100 volts. The voltage deviation of 5 to 10 volt is not observable in the figure. Under similar system working conditions, a symmetrical fault is introduced and the results obtained are shown in the figures. The system is subjected to the fault type of line to line in the B C phase. The dip in the stator voltage in the phase B and C is 50% of the nominal value for 5 cycles, that is 0.1 second duration. There is even greater disturbances in the RSC and GSC current when subjected to asymmetrical fault as seen in figure. The reason for the DC link voltage shoot due to the limitation of the converter to cope up with the high inrush current flown through the rotor. Further, line to line fault allows asymmetrical variation in voltages, and the presence of higher negative sequence component leads to larger variation in active and reactive power as presented in the figure. A clear distinction between the symmetrical and asymmetrical fault is as shown in the figures, which highlights the considerable difference in flux, speed of the rotor and in the DC link voltage variations. In asymmetrical fault, the reason for increased variation in flux during the transient period is due to the presence of negative sequence component of voltage in the stator, which induces relatively higher rotor voltage. The settling time for the speed seems to be very large in the case of asymmetrical fault due to the effect of negative sequence component. This leads to the larger variation in the flux, which further increase perturbation in the RSC current, and the extra power accumulated in the rotor causes more perturbation in the speed. In asymmetrical fault, the reason for increased variation in flux during the transient period is due to the presence of negative sequence components of voltage in the stator, which induces relatively higher rotor voltage. In this work, the analytical view of PHIL experimentation of DFIG WTG under the symmetrical and asymmetrical fault is shown in detail. It can be deduced from the results that the asymmetrical fault greatly influence the transient response of the system. The asymmetrical fault effect can be summarized in the following terms. There is a almost twice variation in flux while the speed varies drastically. Second, there is a increased disturbance in the RSC and GSC current. There is a rise that is shoot up in the voltage of DC link due to the accumulation of energy at the DC link capacitor. The huge fluctuations in active and reactive power injected to the grid also indicates the severeness of the asymmetrical fault. To conclude, In this lecture, we have learned PHIL experimentation for symmetric and asymmetric fault analysis of grid connected DFIG wind turbine in detail. I am confident that this content may encourage you to carry out certain laboratory experiment and further research in the same field. Thank you.